Okay, good morning, everyone. Thanks for coming to the earlier session of the last day. My name's Lucinda and I work at the University of Sydney with Peter Tuthill, Barnaby Norris and Eckert Spalding on the Vampires instrument, which is a differential polarimeter mounted on the SCExAO bench at SUBARU telescope. You can go to the next slide. So the context for this work, which I don't need to go over in great detail because we've talked about it a lot this conference, is that we don't have a complete picture for how evolved stars lose mass. And specifically, we don't have a complete picture for what drives the stellar wind. And this problem gets worse and worse the bigger stars we consider. And for things like red supergiants, none of the mechanisms that can be used to explain AGB wind driving seem to add up to something large enough to explain RSG wind driving. So from an observational point of view, one critical region for understanding this is to observe in the inner core of the mass loss region at what we call the wind base. So we're looking to visualize and observe what is actually happening as the dust is initially conceived at that inner region in the wind base. From an observational point of view, this is very challenging because if you try to make an image in that region, you're completely blinded by the strength of the central star and you can't resolve the dust surrounding the star. So what Vampires does is it uses polarimetry to overcome this. And this is a common technique. Essentially, it takes advantage of the fact that stars are weakly polarized compared to the light that's scattered from this circumstellar dust. And so effectively, we buy ourselves the world's best coronagraph and we get a really nice image if the target is appropriately sized where the star is basically blocked out. We can go to the next slide. Thank you. So Vampires combines polarimetry with non-redundant aperture masking. Non-redundant aperture masking, or NRM, is essentially single telescope interferometry. People get mad at this because what we do is we take a mask like this one and we basically block out most of the photons on a single telescope. It's very counterintuitive because when we think about interferometry, we normally think about really long baselines, and that makes sense to all of us because we make the baseline bigger, we can resolve smaller stuff. So it's not super intuitive why doing something like this would increase our ability to make any measurements. We're not increasing the longest baseline. We can't change the size of the tertiary mirror. We're not changing the wavelength. The answer is, and if you can remember this phrase, you're doing better than most of us, is that we don't have redundancy noise when we do interferometry. So when we put an aperture mask on a single telescope, we remove this huge source of noise that allows us to measure the Fourier components that the mask selects out with much higher signal to noise than we would have gotten in an image. So we get higher signal to noise observables. The other side of that is then we have to reconstruct an image from these things that we call interferometric observables, visibilities, and closure phases. So Vampires combines those two techniques to give you sub-diffraction limited measurements of polarized light within this innermost region. And it does it over multiple optical wavelengths. And so I refer to this as a spatiospectral coverage of this region. And so we can go to the next slide. Thank you. So before I show you what the NRM plus polarimetry data product looks like, I think it's useful to show you what would happen if we took a direct image. And this is absolutely one functionality of Vampires. For a lot of targets, we're better off making a direct image. So in Stokes' eye, which is what we normally observe, the star's still there. That's what we'd normally see. The dust is too faint to see it. And then you look through your polarized filters and all of a sudden you can resolve the shape of the circumstellar envelope and the dust is gone. And so to make these measurements, we use a Stokes formalism, which is just a convenient basis to represent polarized information. So Stokes' I represents our intensity, and then Q and U are orthogonal linear polarization components. And we refer to that whole data product as a Stokes vector. So every point along our wavefront can be represented with a Stokes vector. We can go to the next slide. So then if we look at the NRM product, for Stokes' I, we get these visibilities, which are probably familiar to any of you who've looked at any interferometry, but for Stokes' Q and U, we get a differential product because what we've done, just as to make our, actually, can you go back a slide? Thank you. Just as we've done to make these polarized images, we've subtracted two orthogonal linear polarization states. Okay, you can go forward to slide. In visibility space or in Fourier space, we divide those equivalent measurements of visibilities. So what we get out is a complete description of the polarized material around the star with that subdiffraction limited resolution that interferometry gives us. And we also get closure phases and bispectral measurements. They're just not as nice to plot, so I haven't plotted them here. We can go to the next slide. Thank you. So what we've done in the past to measure this, because this is a huge parameter space, we want to understand what is in this region and where it is. And we also have 4 wavelength bands to cover. So we can look at the spatial distribution, and then by looking over multiple wavelengths, we get the spectral bit out, and we can talk about how big the dust grains are and what they're made of. The first thing we do is we ignore the spectral bit, and to 1 wavelength, what we've been doing is just fitting to the circumstellar geometry. But as that parameter space is really big, it requires us to make a lot of assumptions, and they're usually assumptions about the scattering symmetries. So we might assume a Rayleigh isotropic scattering function, we might assume a Mie anisotropic scattering function, and then also make assumptions about how optically thin or thick the material is. So what we were doing is making an assumption of the scattering, designing a bunch of these circumstellar morphologies, and then fitting them using a differentiable Ford's modeling framework. We would then later take that morphology, plug it back into MC-FOST, and then deal with the chemistry. And this worked really well for a long time, but there are obvious problems with this, right? We have to assume a certain scattering function, and also implicitly in doing so, we've assumed that it's homogeneous across the whole regime, which we know from a lot of studies is probably not a realistic assumption at all. If this conference has taught us anything, it's this: these regimes are much more complex than perhaps we've thought in the past or modeled them in the past. We can go to the next slide. Thank you. So this worked really well, but it all kind of fell down with this data set for red supergiant MuSEP. You can click about 5 times, I think. Let's find out. 1, and then stop there. Great. So this is a data set from MuSEP. We took both of these sets on the same evening. They're separated by 120 minutes and about 40 degrees of parallactic angle rotation. And in summary, what we see is this quite drastic phase shift of some of these features within our signal, but it's not uniform in azimuth. So the green line, looking at that inflection point here, moves by about 0.3 radians, but then this one out here describing this minimum doesn't move. And so without going into substantial detail, the reason that we see that is essentially that we're breaking these symmetry assumptions we've made about our scattering functions. So this data set ended up showing us that these assumptions aren't tractable for really complex targets, or the other way to think about it is that we're resolving far more asymmetry and far more detail in scattering asymmetry in this region than we previously thought we could with this instrument. We also at this point did a very extensive instrumental polarization search, because instrumental polarization looks quite similar, only to find that this is in fact astrophysical and quite an interesting data set to model. We can go to the next slide. So this is a point at which it would be very useful to have an image reconstruction algorithm. We often use image reconstruction interferometry where we don't really know what's going on, and we want to converge on a plausible image that might drive our modeling. So image reconstruction is a very ill-posed non-convex optimization problem. Fundamentally, we're taking maybe hundreds of visibilities and we're trying to re-represent them in an image basis with far more pixels than we had original visibilities. So from an information theory point of view, it's quite a dangerous exercise, and we have to be very careful not to over-represent the information content in our image. So we can think of it as summarized by this nice equation. The goal of the algorithm is to optimize or minimize the difference between the observables we see on sky, so our visibilities and closure phases, and then the difference between that and the visibilities and closure phases we would remake from our reconstructed images. So our images need to reproduce our observables, that makes sense. But because the problem's so ill-posed, there are infinite images that could do that, we have to drive the algorithm heavily with a form of regularization. That basically enforces that we want the images to be things like smooth. So you may have heard of the maximum entropy condition as an example. That's basically just Occam's razor. And there are a bunch of other statistics that regularize the image plane that we hear about in this field. The thing about polarimetric image reconstruction that makes it more challenging is that I would argue these aren't really images. I would argue that they're spatial maps of vector components. And what that means is that all of the pixels in each of these polarized images not only have a relationship with the adjacent spatial pixels, but they also have this relationship in 3 dimensions with all of their other vector components. And so we have to also take into consideration some sort of physics-informed regularization. The scenes have to be realistic, and they have to constrain the physics properly within themselves and within each other. So there's no obvious way to go about doing this, and regularizing for this physics part isn't tractable with something like a radiative transfer model because they don't run fast enough. So you can go to the next slide. What I've investigated within this part of my thesis is the role that machine learning can play in doing this. What we want to do is teach an algorithm to learn a mapping between our observables and the image plane, and we want it to learn that mapping in a way that's cognizant of these regularization requirements. And the theory is that if you only train a neural network to reproduce nice, smooth, regularized images, you should get exactly the same regularized images out when you apply it in practice. And we've used a two-stage framework. The first part that we've used to learn that mapping is a convolutional neural network. So they're like our very common image-based neural network structure for various reasons. And then the second thing that we've done is we've iteratively fit that CNN. What that allows us to do, and I'll go into a bit more detail later, is to introduce our experimental errors and to make sure that our images both have the right sort of statistics, but also fit our data well. And then again, just like we did originally with a geometric model, we chuck that back into MCFOST at the end. So nothing's being used to do physics immediately out of this. We're narrowing our parameter space. You can go to the next slide. So this is the framework. We're going to take our observables, pass them to our CNN and ask it to reconstruct these polarized images. We're then going to take the CNN reconstructed images, the original observables, and pass them to the iterative fitting, and that should give us a better image. You can go to the next slide. Fantastic. So to make the training set, I built a custom data set of MCFOST models. I randomly inserted a bunch of Gaussian blobs. The images are quite oversampled. So the pixel scale of vampires is about 6 milliarcseconds per pixel. I made these 1 milliarcsecond per pixel because I want them to be really nice and smooth. And I built them of blobs, the idea being that I want my output examples to be nice and diffuse. And I put the blobs everywhere and sampled them uniformly so they appropriately cover the image space and also the expected dynamic range of the observables. You can go to the next slide. So here are some, and I think you can click twice now. Yes, great. So here are some examples of how the CNN performed initially. The top row are the truth images I asked the CNN to reconstruct, and the bottom row are what it did reconstruct. And you can see it does a reasonably good job. I've put some arrows here to point out what it doesn't do as well. The tiniest blobs it misses. But as I mentioned before, the tiniest blobs are about 1 milliarcsecond per pixel, maybe 2 or 3, so about lambda on 3D. And this is an 8-meter telescope, so a diffraction limit is about 10 milliarcsecond. Obviously, interferometry allows us to recover sub-diffraction limited information, but we don't want to push that beyond our signal to noise. So part of the way that I designed the CNN architecture is to not reconstruct super sub-diffraction limited things, about lambda on 3D. This is a kind of nice test to show that this regularization as a result of my architectural choices is working. You can go to the next slide. So then we implement the deep image prior paper as part of our iterative fitting. Essentially what the deep image prior paper tells us is that the power of CNNs doesn't just come from their ability to learn from big data sets. If you have a CNN and you use the right architectural choices, as a result of the way convolutional neural networks share kernels across the image plane, they can learn from the information they have to learn things that they do not have. So the example, thank you, I'll probably run slightly into my question time. The example given to us in this paper is that from random noise for a single example, a CNN is asked to reproduce this image of a foyer with a bit cut out. And I think you can click now. What it actually does is this, and the reason it does this and fills this in is that it has to learn kernels that share the statistics across the whole image plane. And so the statistics here do not generalize out here. And this tells us, and this is a function of the architectural decisions, this tells us that CNNs can learn generalizable statistics from a single example and challenges that idea. So you can click once more. So what we're going to do in the context of our work is we're going to pass observables to the iterative fitting. You can click again. Our CNN predicted images are kind of like our image with the bit cut out. There's something missing, but we're going to suggest that that missing information can be inferred from the statistics of the images we do have and our observables, and that should give us a better image. You can click now and click again. So here is an example of, this is a validation example. These were the true images. These were what the CNN initially predicted. So this is our starting point prior to iterative fitting. You can click again. These are the observables for the true and the CNN predicted images. This is just to show you that functionally the CNN does get a lot right. You can click again. A better way to plot that is as a residual. So you can see it gets Stokes' I right, but there's some fundamental bias, offset, and scatter in our polarimetric visibilities. Now we let the iterative fitting loose, and what we want to see is that that scatter reduces and the bias converges towards the black line, which is just y equals x. So you can click again, and that's exactly what it does. So that's a nice test on our validation set, and then click again. Here were our closure phases and bispectral measurements for the same example. You can see there's a lot of scatter when we originally used the CNN and some offset. You click again, and then that completely disappears as a result of our iterative fitting. And then you can click again. And the key thing is that this improvement in observables is also associated with the preservation of the nice regularization properties that our CNN was designed to encode. You can click again. The proof is in the pudding, though, because we want to look at a more realistic example that's not from the same spatial basis, so not constructed of blobs. So I built this circumstellar disk in MC-FOST, and I've put in lambda on D here just to give you an idea of the scale of features that we would expect to be able to reconstruct. Here is the CNN prediction of that. And then if you click again, here are the observables. So again, some scatter and offset, click again. And then we see that for this example that's taken from a different spatial distribution, we see the same positive impact of the iterative fitting. There are still some residuals in here, but overall, I would rather a scatter than a systematic offset. We can click again. And these are just the results again for the closure phases and the bispectral measurements. Click again. What's really interesting about this result, though, is that this improvement in fit to observables we see from our disk is also associated. Before, in the example I showed you before, I said, great, it doesn't destroy the image. Here it improves the image. It actually paints in some forward scattered flux that was missing from the original CNN prediction. So this is a really interesting result because it shows us the iterative fitting is able to draw on those pre-learned CNN kernels that have inherently regularized and encoded the physics of the examples that we've considered. You can click again. So with that, I'll leave you. We've got some ideas for future work, but I might just put that up there because I'm over time. This work is always conducted as part of a very large team, which I'd like to acknowledge. And thank you. I'd welcome your questions.
That filling in of the physics knowledge doesn't it seem extremely dangerous? So many times we see things in images we're sure is something because our brain completes because we know what it looks like. And this looks like it's doing exactly the same.
This is a really good question and is fundamental to, like, philosophically, how much should we believe image reconstruction? So my answer, I guess I have two answers. The first is that this is an example for which we have the ground truth. So we know that in an ideal world, the best reconstructed image is meant to have flux there. That's part of the information. And we also know that it's not subdiffraction limited. So it's contained in the information given to us by our original observables. That would be my answer. As to whether or not we should trust image reconstruction in general, I think as long as we regularize properly and we think very carefully about information theory in the process, it's a helpful tool to help us constrain a distribution, but I don't go and calculate a grain size from this image, right? I go and plug it into MC-FOST and then see if it stands up to my spectral check as well. Does that answer your question? Yeah, cool.
Can you not give us a peek at what happens when you apply this to your data?
I wish. It's not ready yet. I've got to retrain my algorithm on a slightly different basis of examples because the MuSEP, I can't go back. I think what's going on, I think there's a ring, some sort of consistent ring and an optically thick blob. And we have very high polarization amplitudes around MuSEP, so I need to retrain my network to consider those. All of these machine learning algorithms only work well if you apply examples that are within distribution, but we know what's within distribution because we've trained it, and the distribution's defined by the range of our observables. Yeah.
I was just wondering, what kind of loss functions have you defined and how do they impact then the reconstruction?
So I use a mean squared error for the CNN reconstruction. We played around with a lot of different loss functions. What we found the most impactful, the only thing we ran into that really was affected by this was the Stokes' I image because it's so high contrast. So we actually pass in our training set the log of the Stokes' I image so that the dust and the star are both nicely displayed in the image. There's not a kind of dynamic range problem. And the mean squared error cares more about higher amplitude things than lower amplitude things if you compare it to something like mean absolute error. So the image quality was the best for the mean squared error, but then for the iterative fitting, we use a chi-squared. So we just add in the experimental errors, which allows it to only change things associated with a higher signal to noise.
And have you considered or tested potentially loss functions that are based on physical arguments? For instance, when we have been working on the POM reconstruction, so the Bayesian technique, we there have one of the options there is to include loss functions, which, for instance, take into account conservation of energy, conservation of hydrodynamics, and that helped a lot into having better reconstructions.
That's a really interesting question. I think from the perspective of this study, we were interested in image plane regularization and putting the emphasis on the convolutional neural network to learn the physics and to learn to regularize the output images in a way that was cognizant of the physics. We were interested in testing whether or not that was possible. So I haven't thought too much about that. Probably the next thing I would do before thinking about that is to embed an error-aware network in place of my CNN. So use diffusion modeling or a Bayesian neural network. And that would allow me then to think a bit more about what you're talking about.
Does it? So at the beginning, when you started with a very simplistic approach, basically you had a very degenerate problem, right?
Yes.
There were too many solutions, basically. And now you found something, and with, let's treat it as a black box, something that gives you a unique, effectively, solution. Does it make sense? So if you have, just going back and trying to validate the approach, the number of degrees of freedom that you had, are they matched by the, what I mean? Like, does it make sense that you have completely made the system non-degenerate? Now you have a unique solution.
I think the key thing that using the CNN unlocks, it allows us to reconstruct an image that embeds both the circumstellar morphology and the scattering regime. So those two things constraining it, they're not degenerate in the original approach. It's just that there's no computationally tractable way to forwards model them. Yeah. So they're not degenerate, they're just very difficult to model and to separate. Yeah.